morning, everyone. Now I will be discussing the Lethal theorem. The most significant of Fermat's correspondent in number theory was Bernhard Frenikel de Visée in 1605 to 1675. An official of the French Mint who was renowned for his skill manipulating large numbers, Frenikel's facility in numerical calculation is revealed by the following incident. On hearing that Fermat had proposed the problem of finding cube which when increased by their proper divisor becomes square, as this case with 7 cubed plus 1 plus 7 squared is equals to 20 squared. He immediately gave 4 different solutions and supplied 6 more the next day. The in no way Fermat's equal as mathematician, Frenikel among his contemporaries could challenge him in number theory, and his challenges has the distinction of coaxing out of Fermat some of his carefully guarded secrets. One of the most striking is a theorem which states if P is a prime and A is any integer. Striking is a theorem which states if P is a prime and A is any integer not divisible by P, then P divides A P minus 1 minus 1. Fermat communicated the result in a letter to Frenikel dated on October 18, 1640, along with a comment, I would send you the demonstration if I did not fear its being so long. This theorem has since become known as Fermat's Lethal theorem, distinguished from Fermat's great or last theorem, which is the subject of chapter 11. Almost 100 years were to elapse before Euler published the first proof of the Lethal theorem in 1736. Leibniz, however, seems not to have received his share of recognitions, for he left an identical argument in unpublished manuscript sometimes before 16. We now proceed to a proof of Fermat's theorem. Theorem 5 to 1, Fermat's Lethal theorem. If P is a prime and P times A, then P to the power of P minus 1 is equals to 1, mood P. Proof. We begin by considering the first P minus 1 positive multiples of A, that is the integers. A, 2A, 3A, ellipses P minus 1 times A. None of these numbers is congruent modulo P to any other, nor is any congruent to 0. And that, if it is happened that RA is equals to SA mood P, R1 less than or greater than R, less than S, and less than or greater than P minus 1. Then A could be cancelled to give R is equals to S mod P, which is impossible. Therefore, the above set of integer must be congruent modulo P to 1, 2, 3 to P minus 1. Taken in some order, multiplying all these congruences together, we find that A times 2A times 3A to P minus 1 is equals to 1 times 2 times 3 to P minus 1 mod P. Whence, A to the power of P minus 1, P minus 1 permutation is equals to P minus 1 mod P. Once P minus 1 permutation is cancelled from both sides of the preceding congruence, this is possible since P by P minus 1 permutation, our line of reasoning culminates in A to the power of P minus 1 is equals to 1, mod P, which is Fermat's theorem. So, mao na siya gitawag og Fermat's theorem. This result can be stated in a slightly more general way in which the requirement that P by A is dropped. Corollary. If P is a prime, then A to the power of P is equals to A mod P for any integer A. Proof. When P by A, the statement obviously holds, for in this setting, A to the power of P is equals to 0 is equals to A mod P. If P by A, then in accordance with Fermat's theorem, A to the power of P minus 1 is equals to 1. When this congruent is multiplied by A, the conclusion A to the power of P is equals to A mod P follows. There is different proof of the fact that A to the power of P is equals to A mod P involving an induction on A. If A is equals to 1, the assertion is that 1 to the power of P is equals to 1 mod P, which is clearly true as this case A is equals to 0. Assuming that the result holds for A, we must confirm its validity for A plus 1 in light of the binomial theorem. A plus 1 times P is equals to A to the power of P plus P over 1. A times A to the power of P minus 1 plus 2 plus P over K times A to the power of P minus K plus ellipsis plus P over P minus 1 times A plus 1, where the coefficient P over K is given by P over K is equals to P permutation over K permutation, close and open parenthesis, P minus K permutation is equals to P times P minus 1, ellipsis P minus K plus 1 over 1 times 2 times 3 to K. Our argument hinges on the observation that P over K is equals to 0, mode P for 1 less than or equal to K, less than or equal to P minus 1. To see this, note that K permutation P over K is equals to P times P minus 1, ellipsis P minus K plus 1 is equals to 0 mode P, by virtue of which P such that K or P of times P over K, but P such that K implies that P such that G for some satisfying 1 less than or equal G less than or equal K less than or equal to P minus 1. An absurdity, therefore, P such that P over K, or converting to a congruent statement, P over K is equals to 0 mode P. The point which we wish to make is that A plus 1 times to the power of P is equals to A to the power of P plus 1 is equals to A plus 1 mode P, where the rightmost congruent uses our inductive assumption. Thus, the desired conclusion holds for A plus 1, and in consequences for all greater than or equal to 0. If A is a negative integer, there is no problem, since A is equals to mode P for some R, where 0 less than or equal to R, less than or equal to P minus 1. We get A to the power of P is equals to R to the power of P is equals to R, or is equals to mode P. Fermat's theorem is a tool in testing the primality of given integer n. For, if it could be shown that the congruence A to the power of n is equals to A mod n fails to hold for some choice of A, then n is necessarily composite. As an example of this approach, let us look at n is equals to 117. The computation is kept under control by selecting a small integer for A. Say A is equals to 2. Since 2 to the power of 117 may be written as 2 to the power of 117 is equals to 2 to the power of 7 times 16 plus 5 is equals to 2 to the power of 7 times to the power of 16, 2 to the power of 5. And 2 to the power of 7 is equals to 128 is equals to 11 mod 117. We have 7 to the power of 16 times 2 to the power of 5 is equals to 121 to the power of 8. 2 to the power of 5 is equals to 4 to the power of 8 times 2 to the power of 5 mod 117. But 2 to the power of 21 is equals to 2 to the power of 7 times 3, which leads to 2 to the power of 21 is equals to 11 to the power of 3 to 121 times 11 to the power of 4 times 11 is equals to 44 mod 117. So that 117 must be composite. Actually, 117 is equals to 13 times 9. It might be worthwhile to give an example illustrating the failure of the converse of Fermat's theorem to hold. In other words, to show that if A to the power of n minus 1 congruence 1 mod n for some integer A, then n need not be prime. As a prelude, we required a technical lemma. Lemma if P and Q are distinct primes such that A to the power of P is equals to A mod Q and A to the power of Q is equals to A mod P, then A to the power of PQ is equals to A mod PQ. prove, it is known from the last corollary that a to the power of q times p is equivalent to a to the power of q mod p, while a to the power of q is equivalent to a mod b by hypothesis. Combining these congruences, we obtain that a to the power of pq is equivalent to a mod p, or in different terms, p such that a to the power of pq minus a. In an entirely similar manner, q such that a to the power of pq minus a, the corollary to theorem 2 to 4, now yields pq such that a to the power of pq minus a, which can be recast as a to the power of pq is equivalent a mod pq. Our contention is that 2 to the power of 340 is equivalent to 1 mod 341, where 341 is equals to 11 times 31. And working towards this end, notice that 2 to the power of 10 is equals to 1024 is equals to 31 times 33 plus 1. Thus, 2 to the power of 11 is equals to 2 times 2 to the power of 10 is equivalent to 2 times 1 is equivalent to 2 mod 31. 2 to the power of 31 is equal to 2 times 2 to the power of 10 times 3 is equivalent to 2 times 1 to the power of 3 is equivalent to 2 mod 11. Exploiting the lemma, 2 to the power of 11 times 31 is equivalent to 2 mod 11 times 31. 2 to the power of 341 is equivalent to 2 mod 341. After concealing to a factor of 2, we pass to 2 to the power of 340 is equivalent to 1 mod 341, so that converse to Fermat's theorem is false. The historical interesting number of form 2 to the power of n minus 2 resides in the claim made by the Chinese mathematician over 25 centuries ago, that n prime, if and only if n such that 2 to the power of n minus 2, and point of fact, this criterion is reliable for all integer n less than or equal to 340. Needless to say, our example were 341 such that 2 to the power of 341 minus 2, although 341 is equals to 11 times 31. Lays the conjecture to rest. This was discovered in the year 1819. A situation in which n such that 2n minus 2 occurs often enough to merit name do. Call compasses integers and should operand whenever n such that 2 to the power of n minus 2. It can be shown that there are infinitely many Sagitta primes, that smallest for being 341 to 561 to 645 and 1105. So that would be all. Thank you.